All right, so the other day we were talking about unbanked curves and how friction is what keeps you in that curve. And if there isn't enough friction, you will obey Newton's first law and you will travel in a straight line at a constant velocity. Okay, and we talked about how our instinct when that happens is to do exactly what is wrong, okay, which is to slam on the brakes and crank the wheel really hard. Okay? If we want to get around an unbanked corner, we want to rely on static friction, okay? Which means the tires do not slide. Okay? They simply travel around the corner and they maintain traction with the road. Okay? So what we're going to do is I'm going to show you, I was talking about Canada's Worst Driver. I found the video, so we can have a little laugh. Okay? It's not really at other people's expense, but kind of. Okay, so static friction, that's what we want to have when we go around a corner. So what that means for us then is that our centripetal force, which is our net force, is being provided by the force of friction. Okay, that's the sum of all forces part of a banked curve question. Okay, we have to, in this case, kind of memorize what acts as the centripetal force in this situation. It's friction. Okay, because the curve is flat. There's no normal force like we talked about the other day, okay, with those banked curves. Right, which I'm going to show you another one which was crazy that this guy thought of this and it was amazing. Okay, so we got Fc equals Ff. Now our formulas there are mv squared over r, that's Fc, equals mu times the normal force. Now, because the corner is flat, the normal force is equal to what force? The force of gravity. Okay, so I can actually just take this out and say mu mg. What's on both sides of this equation?
Mass.
Yeah. So what does that mean for any corner?
Mass doesn't matter.
Yeah, it means that mass doesn't matter. Okay, that's why when you go on an exit ramp, there aren't 100 different speed limits. Because if mass mattered, you'd have to have a speed limit for every mass. Then you'd have to know the mass of your car, which probably a lot of people don't. Okay, it's not something we typically worry about because in most situations other than stopping, mass really doesn't matter that much. Okay, so if I want to manipulate this to figure out how fast I can take a corner, I just have to solve for v. Everybody okay with that? So what you see in this picture here is what car makers call the skid pad test. Okay? The skid pad test is what tells them how well a car corners or handles. Okay? And so they just have a circle drawn on the ground and they have a test driver take the car around that circle at an ever increasing speed until it skids out. Okay? Once it skids out, then they can calculate the cornering force the car is capable of. Okay? A typical passenger car usually has a cornering ability of somewhere around 0.85 Gs. Okay? So about 85% of gravity. A taller vehicle like an SUV or a truck, it's going to be a bit lower, probably like 0.8, 0.77, something like that. A cube van, okay, is going to be like 0.6, and it's not because of the lack of friction. It's because of where their center of mass is. Okay, they don't actually lose cornering because they actually lose friction. They lose cornering because they tip over. Okay, if you drive anything tall, a truck, an SUV, even a van sometimes have a thing on the back of the sun visor that warns that if you take a corner too fast, this car can roll. Okay, so I want to solve for v. So I'm going to multiply both sides by r. M is going to cancel because it's on both sides. And then I'm going to take the square root. Okay, so v equals the square root of mu. You'd be surprised how often that comes up. Okay, mu. All right, so v equals, in this situation, we're looking at this in dry weather, where our coefficient of friction is 0.9, so quite high, and icy weather, where it's the opposite of that. Okay, now, looking at those two numbers, 0.9 and 0.1, okay, so we've reduced the friction by a factor of 9. how many times slower am I gonna have to go? 3 times slower. Remember, it's an exponential relationship, okay? All right, so V is gonna equal the square root of 0.9 times 9.81 times the radius of the corner, which we were told is 50 meters. All right, so we got the square root of 0.9 times 9.81 times 50. All right, so that car can take that corner at 21 meters per second. Okay, under ideal conditions. Right? Under dry conditions, what do we think it'll be? 7, yeah. Right? So if we plug in those same numbers, but with the 0.1 instead of the 0.9, yep, 7 meters per second. Okay, so do we have to take icy corners slower? Of course we do, we already know that. Okay, this is just the physics proof of it. Okay, questions on that? All right, now, I'm gonna show you something that one of my period 2 guys showed me, and it's of this NASCAR race. Remember we were talking about the importance of the bank curves in NASCAR? Okay, I mean, they go really fast, so they use not only the friction on the corner, but also the bank of the corner to keep them in the course. Well, apparently, this guy figured out that he could use the wall as an additional centripetal force, because if his car went into the wall wasn't gonna collapse, the wall was gonna push back towards the center of the circle, which is totally right. It was the last corner, it has to be running into the corner in a race car, it destroys the race car in pretty short order, okay? But he uses the corner as an additional force and flies by 8 cars on the last corner to get himself into the championship round. NASCAR since then has outlawed such maneuvers, okay, because it was brilliant, but also kind of cheap, okay? But it was like really great that he thought of it, because like, holy smoke. Okay, it's also why they weld the doors shut on race cars, and that's why you have to get in and out through the window like the Dukes of Hazzard. Okay. All right, so this is what we just did here, looking at why an unbanked curve relies on friction, okay? But the next kind of curve we want to look at are banked curves, okay? So like the NASCAR corner, like this one, except these guys did not negotiate it correctly, okay? And as a result, they're going sideways. So if you bank a corner, essentially what you do is you turn it into an inclined plane, which brings different forces into play. So if we recall what an inclined plane looks like, and you would never bank a corner like this, okay? So we'd have this angle of bank here. Now, if I put a race car on there, and I just put it on there, the forces are gravity, normal force, and F parallel, okay? If it's just sitting there. But when you're driving it around, if this is now a corner, okay, and you're driving it, you have inertia. And that inertia puts additional pressure on the surface of the road, which means now the surface of the road has to exert more force back. So now this triangle changes. When this becomes a corner that you're moving around, normal force becomes the biggest side of the triangle, and it shifts. And it ends up looking like this. You got normal force there, you got gravity here, and you've got a force that's directed towards the center of the circle. If it's directed towards the center of the circle, it's FC. Okay, everyone kind of follow me there? So realistically, that means that the faster you go, the harder the corner pushes back. That's only good so far though, okay? At some point, you are also relying on friction. And once that fails, the force from the corner is not gonna be sufficient. Okay? Has anyone ever watched the indoor cycling where they go on those really steeply banked tracks? It's the same thing, like they're almost vertical and they're going around and around really, really fast. Okay? So yeah, this is how it works. So we got normal force on this side, okay? This angle here is the same as this angle, okay? And then this side here is FG. So we know how to calculate this side, and we know how to calculate this side. Okay, is everyone okay with what I'm doing there? Those two formulas? Okay, so I should be able then to calculate the speed at which I can take a banked curve based on this angle. Okay, so what we're going to look at here is kind of the derivation of that formula. All right, and as we said the other day, the same thing is true for how a plane turns. Okay? A plane can make slight course corrections with just the rudder on the tail, okay, like a boat. Right? But if it wants to make sharp turns, it banks its wings, because then as soon as we bank the wings, instead of the lift being vertical, the lift is now angled and has a horizontal component that points towards the center of the circle. Okay? It also means then that the vertical force against gravity is decreased, okay? Which means the plane is also going to be doing what while it's turning? Falling, losing altitude. Okay? It may not be falling. You never want to use the word falling. Okay, the plane will definitely be losing altitude. Is there a bank situation where the plane would literally be falling?
Yeah.
What's the angle of bank?
If it was completely like this.
You bet. If it goes totally horizontal, none of the lift is lifting anymore. Okay, it's all directed towards the center of the circle. So you turn really sharp, but at the same time, you are falling. Okay, there is no lift at that point, and you are falling. Okay, and the plane will lose altitude quickly. It's actually one of the maneuvers that fighter pilots use to kind of get in behind their target. And you could see it, they had a scene of it in Top Gun where they were doing the Cobra maneuver, they were spiraling around each other. And if they get into a bank like that, they drop quickly, which can get them into a position for a shot on their target. Okay.
Pilots have to take physics.
Oh yeah, it's a big part of it. Okay, so with a banked curve, this is what we got. It's a much better picture than my picture. Okay, so we got the car going around the corner, okay, we know the radius of the corner, and these are the forces. Okay, this is the normal force, it acts perpendicular to the corner. This Fn times the cos of theta is going to offset gravity, because obviously you don't fall down through the corner. Okay, and then this little horizontal component here, okay, is going to be our centripetal force. So we could kind of draw it up here, because those two sides would be equal. Right? So that side will represent Fc. It's the opposite side to the angle. Everyone okay with that? Yeah? Okay. So when we set this all up, okay, we have the opposite side and the adjacent side. Okay, so we would have Fc being the opposite side, Fg being the adjacent side. What trig function is opposite over adjacent? 10. Okay, so Fc over Fg equals the tan of the angle of bank. Right, if I plug in those two formulas, okay, it looks like that. If I divide those two formulas, what I end up with is that the masses cancel and G ends up beside R. And I get the angle at which I can bank the corner. This is a formula that any like urban planner or civil engineer would use when designing an interchange. Unless, well, any interchange, even if they're going to have lights at the top, like all the ones in Calgary for whatever reason. Okay, but if you do any interchange, you're going to use a bank curve because then you don't use as much land. Okay, banking a corner means that you can make the corners tighter, and then you don't use up so much property. All right, so that formula there, that's on your formula sheet. That is the banked curve formula. Okay, we would use it to calculate either the speed at which a banked curve could be taken, okay, the radius of the curve, or the angle at which the curve needs to be banked, okay, for a certain speed. So if a civil engineer was planning out his interchange, then he would know how much room he had, so he'd know what R is, okay? And he would know probably how fast he would want that corner to be rated for. Most interchanges are rated for 40, okay, some for 60, but that it's rarely more than that, it's rarely less than that, okay? And so they would just set it up and bank the corner and build it appropriately. Okay, so this is just the derivation of what we just did there. So the purpose of a bank curve, okay, is not to allow us to go faster around the corner. Okay, it can be a byproduct, but its primary purpose is to give us a speed that corner is safe at, no matter what. No matter what the road conditions are. Okay, that recommended speed sign, because it is recommended, it's yellow, okay, usually. Okay, if you take it at that speed, it could be covered in ice and you'd be safe. Okay, so they're designed and built that way so that they're always going to be safe at that speed. Does that mean you could take them faster under ideal conditions? Certainly. Okay, but as soon as you go faster than that speed, friction is now playing a part in keeping you in the corner. And that's the thing that can vary from day to day. Okay, it can vary from temperature to temperature. The road gets a little bit wet or a lot wet, okay, or it gets a little bit of ice on it, or maybe there's still some of the gravel from the sanding trucks and they haven't cleared it all off yet. All of that stuff can affect friction. Okay? And if you're going around a corner and suddenly there's a patch of, maybe a puddle or something like that, now suddenly your friction is going to change. And if you weren't going the recommended speed, you may not have sufficient centripetal force to keep you in the corner. And you'll be doing what that race car guy did, testing the guardrail. Okay. All right. What do we got for time here? So if we wanted to determine the angle at which a frictionless curve should be banked for a speed of 35 meters per second, which is ridiculously fast, okay, and a turning radius of 550 meters, okay, we would use this formula here, and we would solve for theta, which simply means we would have theta being equal to the inverse tan of v squared over r times g. Plug in those numbers. 35 squared divided by 550, which is a really big corner, okay, times 9.81. Okay, if we do that, we should get around 13 degrees. That is definitely not an exit ramp. Okay, that's a racetrack. 13 degrees is quite a bit more than you would think. All right? Like when we look at 13 degrees, you're like, oh, that's not very steep, right? Because 90 degrees is vertical, 13 is not much. Most steep hills, like the roads on a steep hill, are less than 10%, or less than 10 degrees. Okay? If you make them too steep and they get a little bit icy, everybody slides down. Anybody watch the show on Discovery Highway Through Hell? It's all about the Coca-Cola and the tow trucks on the Coca-Cola. The Coca-Cola has some really steep sections, and every time they get a snowstorm, semi-trucks end up sliding back down. Okay? There's places where they have to pull up and put chains on their wheels so that they don't slide, okay? But inevitably people will skip the chain up area and then they end up sliding down and they have to get towed up, okay? Things like that. So we don't typically make our roads very steep, because if we do, they'll be virtually impossible to traverse in less than ideal conditions. Okay? So if you are going up a really steep hill, it might be 8% grade, so around 10 degrees. Okay? And that would feel steep. All right, questions on the bank curves? Okay, we're not going to do this problem, but we're going to talk about it because it's actually taking a step back. Anybody ever get a rock in the windshield? Okay, when does that usually happen?
When you're driving on gravel.
Okay, it could be when you're driving on gravel, but I actually got the majority of mine on pavement.
Big trucks are in front of you.
Could be a big truck in front of you. Okay.
Tends to be on like the highway.
Yeah, typically it's gonna be on the highway, or at least you're going probably more than 60 kilometers an hour. Okay, but the car in front of you that spits the rock, what is it doing when it spits the rock? Is it traveling at a constant velocity or accelerating? it's accelerating. If it's traveling at a constant velocity, the force keeping the pebble in the tread of the tire is constant, and so it's not gonna lose it, okay? But while it's accelerating, if it's going fast enough, the friction that's holding that pebble in the tread of the tire may not be sufficient to hold it in the tread of the tire anymore, okay? And that's when it'll be ejected. So, if you want to avoid getting rocks in the windshield, give yourself lots of space when the car in front of you is accelerating. Okay, or even changing lanes, okay, turning a corner, any of those things can change the centripetal force, the friction in that tire, because as your tire interacts with the road, its shape changes a little bit. Okay, and when that shape change happens, it could open up the tread a little bit, reduce the friction, and the rock comes out. Okay, so what happens is, where is that rock going to get dislodged? Typically,
Just after the bottom.
just after the bottom. Okay. Now, if you've just gone mudding and your wheels are covered in mud, that comes off everywhere. Okay, if you've ever heard what it sounds like on the inside of your fender well, okay, that comes off everywhere. But rocks that are typically lodged in the tread get dislodged here because it's right after the wheel has interacted with the road. Okay, and that flattens the tread a little bit and changes its shape. So it's always going to be ejected right there. Okay, and if you are in the wrong place, you will get that one in the windshield. Okay? There are actually lots of places where they have regulations for semi-trucks and lifted pickups having mud flaps that have to be X distance off the ground so that they actually catch the rocks when they're spit, because there's pretty much an optimal angle that they come out at. Okay? Arizona is one of the places that has one of those rules. Okay? And if your mud flaps are too short, you can get a ticket. We don't have those rules here. You don't have to have mud flaps at all here. Okay? Which is why the glass companies do so well here. Okay? Plus we have winter where there's tons of rocks on the road. All that good stuff. Okay. Skip that one. Okay. No, we'll do those here. All right, let's try this one. So this one's easier than what we've just done. Okay, we want to determine the magnitude of the centripetal force. Why did they say magnitude?
Because they don't have direction, because the direction is always changing.
Right. Well, it's not so much that the force is always changing, but because it's centripetal, they already told us the direction. It's towards the center. That's why they only ever ask for the magnitude. Okay, so we're looking for the magnitude of the centripetal force of the wheel or the rim of the dragster's wheel, okay, on the tire, right? Because as your tire is spinning, there has to be a force that holds the tire on. Okay? If it's not, it'll come off, it'll break the bead, and it'll come off, and then your wheel and your tire don't work together anymore, okay? Which is bad. So we want to figure out how much force is required to hold the tire on the rim. They tell us the mass, 45.0 kilograms. Okay, the radius of the tire, 0.480, okay, meters, and the speed of the tire, 30.0 meters per second. Okay, we're looking for FC. Is this going to be an easy problem? Right, I just have to plug into the formula, right? Everything's already there. I don't have to manipulate because I'm looking for FC. All right, so 45 kilograms times 0.480, times 30 squared over 0.480. Is that a lot? It is. There's a lot of force between your tire and the rim, especially because when you accelerate, there's a torque there, okay, that your tire has to hold on tightly. Has anyone ever seen how they put a tire on the rim? Okay, most of us don't ever kind of watch that process, but so what they do is they kind of put some stuff around the inside of the tire, a bit of an adhesive, and then they very quickly inflate the tire, and the air pushes the tire against the rim. Okay, and that's the bulk of what holds your tire on, is just the air pressure inside, pushing the tire against the inside of the rim. Okay, and so if anything happens to break that bead, if your tire gets flat, okay, then there's not enough pressure there to hold the bead, and the tire can come right off. Have you ever seen anyone who's been driving with a flat tire? Okay, you can see the tire gets shredded really fast, okay, because it comes off the bead, it gets wrapped around, and it gets just torn up. Okay, so there's a lot of force that's required for that. Okay, I would like you guys to try question number 1 and question number 2. We definitely got time for that. Okay, so let's do those two. They're easy. Okay, they're not like the bank curves and unbanked curves. They're easier than that. Okay, let's have a look at the first one here. So, an intake fan blade on a jet engine has a mass of 7.50 kilograms. Okay, so they tell us what the mass is, 7.5 kilograms. As it spins, the middle of the blade has a speed of 365.9 meters per second. Okay, and it is a distance of 0.737 meters from the axis of rotation. Why does it have to be in meters? What was the speed in? Meters per second, and my units have to match, okay? So I just convert that to meters really quickly, okay? What's the centripetal force on the blade? Fc equals mv squared over r, okay? And I know that on your formula sheet, it kind of looks like this, okay? And that's simply to remind you that what we're really doing is multiplying mass times acceleration. Okay? But because they're all three being multiplied and divided, it doesn't really matter what we do there, and we just always write the m and the v together on top. Okay? All right, so all we have to do with this is plug in our numbers, so 7.5 times 365.9 squared, okay, divided by 0.737, and we should get 1.36 times 10 to the 6 newtons. Is that a lot of force? It is. The machining and fabrication stuff that goes into building jet engines is very, very precise, okay, and it's very, very strong. They have to use aluminum or titanium, lightweight materials that are very, very strong, okay, for those types of situations. All right, and then for number 2, we have the pebble, which is 2.1 grams, but they gave it to us in kilograms, which is good, that's what we need, is stuck in the treads of a dirt bike's wheel. The radius is 23 centimeters, that's got to be converted to meters, okay, and we know the centripetal force, we're looking for the speed. So Fc equals mv squared over r, solving for v, multiply by both sides by r, divide by m, square root. Okay, so 0.23 times 0.660 divided by 0.0021, okay, that should give us 8.5 meters per second. Okay, on Monday, we'll be looking at doing some problem solving to do with bank curves, unbanked curves, centripetal acceleration, that kind of stuff. And then we'll probably start artificial gravity. And then we'll be doing another lab, I think I have a book for Tuesday, okay, on centripetal force and